Hi everyone, my name is Lloyd Pellatt. I'm a PhD student in the Wearable Technologies lab at the University of Sussex, and I'm going to talk about our recent work on deep neural architecture search for wearable human activity recognition. So I'll start by briefly going over the motivation for our work. As we know, wearable devices with lots of sensors are becoming increasingly widespread, from smartphones to smartwatches, fitness trackers and earphones. These devices give us a wealth of sensor data which can be exploited to offer context-specific services to the user for many applications, from smart health to security. And in many cases this kind of behaviour takes the form of a time series classification problem, where we want to recognise certain events from signatures in streaming sensor data. One of the most powerful methods that we have for performing classification like this is deep learning, which is increasingly being adopted as a standard approach to sporadic activity recognition. This is one example of a fairly typical DNN architecture for wearable activity recognition, DeepConvLSTM. Segmented sensor data is passed through a convolutional feature extractor with 4 layers, followed by 2 fully connected recurrent layers, and finally a softmax layer, which maps the output of the recurrent layers onto the number of classes in the dataset, where the largest activation of an output unit indicates the predicted class of the input sample. The parameters of each layer are then optimized by gradient descent to minimize the loss between the predicted and the actual label. And through this process, DNNs can extract features automatically from raw data, which saves a lot of effort and domain knowledge which is typically required for feature engineering. With that said, designing a deep neural network still requires many choices to be made about parameters like how many layers to include in the network, how many trainable parameters per layer, what connection scheme to use between the layers, and so on. We found that a wide range of choices for these parameters exists in the literature, and rarely any kind of systematic justification is given beyond a grid search over a limited search space. So neural architecture search methods have been proposed in other fields to perform a guided search of the space of possible network architectures, based on techniques including reinforcement learning, genetic algorithms, and gradient descent. These all very generally involve iteratively designing DNNs by a process of sampling from a search space, evaluating the sampled architecture on a target dataset, and then improving the design, whether that's by gradient descent in the case of differentiable architecture search, maximization of expected future reward in the case of reinforcement learning, or by selection, mutation, and crossover in the case of genetic algorithms. And now I'll briefly summarize our approach to neural architecture search with deep Q learning. So first, we sample layers using a deep neural network known as a deep Q network, where the input is the layer index, and the layers are selected from a search space described by this table, where we can choose for each layer the operation to perform, the kernel size if applicable, the predecessors which determine the connections between layers, and the number of units. We repeat the sampling until we reach the terminal layer or the maximum index, and then we incorporate the feature extractor into a classifier network, which includes an LSTM recurrent layer for temporal processing and a softmax output layer. We train the classifier to identify activities in the target dataset, and then we test it to get a reward which is used to train the deep Q network to generate better networks. Since each classifier network takes a long time to train to convergence, we use a performance estimation strategy to predict the converged performance of the network by looking only at the first few training epochs, and then use this predicted value as the reward function for the EQN. We compared several methods for predicting this performance, validated on a dataset of 5,000 randomly generated networks from the search space. More technical details can be found in the paper, and also in an extended version of this presentation, which will be hosted on YouTube. So now I'll very briefly summarise the key results here, but again, if you want more in-depth discussion, you can check out the paper and the supplemental YouTube video. This is a plot showing the correlation between the actual testing F1 score and the prediction from some of our models on the randomly generated set of 5,000 classifiers. So each section here represents 20% of those tested classifier models, arranged by F1 score from the bottom 20% on the left in red to the top 20% on the right in green. The leftmost marker in each section is the baseline, which is just the mean F1 score of 5 epochs. The other markers represent the correlation achieved by the predictors. So what we see is that our predictors can achieve significantly higher correlation with the actual scores on each section, but especially on the best 20% of models, which is good because that's what we're really interested in, because we want to guide the architecture search towards those good models. And here you can see some of the results from our experiments. So the top three models here are a few benchmarks. DeepConvLSTM is a state-of-the-art model, and MaxFF and MaxWide are high complexity benchmarks representing the deepest and widest networks we could generate within the search space. We found that our NAS-generated networks achieved the best accuracy in F1 score out of all the models we tested, and the random search produced models which are almost as good but took up to 10 to 20 times longer than the NAS method with performance prediction. So in conclusion, we proposed a method for designing convolutional feature extractors for deep recurrent neural networks using deep Q-learning. And we show that even using a random search of a well-designed search space, it is possible to find networks which achieve close to state-of-the-art performance. And using architecture search with neural regression-based performance prediction, we were able to find marginally better results in just 5 to 10% of the search time. This shows the potential of deep Q-learning based neural architecture search to automate design of deep neural networks for wearable activity recognition and to advance the state of the art. Okay, thanks for listening, and again you can find much more technical detail and discussion of our results and future work in the extended version of this presentation on YouTube and of course in the paper.